So we're going to be making a Sudoku solver. Now, if you don't know how Sudoku works, here's a 4x4 example, and the premise of the game is to fill in each and every blank space with a number and fill it in so long that each row, column, and box has unique numbers. Now, what I mean by that is if I write a 1 here, this row is invalid, which makes this entire board invalid. So that can't be here. This 4 would make the entire board illegal because there's already 4 within this column, and writing a 3 here would be illegal because there's already a 3 within this box. Now, the way you typically solve a Sudoku puzzle is by sort of, canceling out which ones aren't possible and then filling in the ones that are only possible. So if you see this 2 right here, a 2 can't go here or here, which only leaves a 2 here. And because of that, that means a 3 can only go here, and that means a 1 can only go here, and so on. And that's how you solve a normal puzzle. But the way we're going to do it is we're going to brute force it. And what I mean by that is we're going to go through each space, and we're going to fill it in with every possible value and evaluate whether that's illegal or not. And there's a better way of calling this. This is called backtracking. So this is what we're going to be doing. And I'm going to first fill in the example here, and then I'll draw it out for you. So we're going to move into the first available space, and we're going to fill it in with a 1. And is a 1 possible? No, it is not. So we're going to move in and fill it in a 2. And is 2 valid in this instance? Yeah, it is. So we can move in here. And now we can fill it in with a 1. And is 1 valid? No. All right. Is a 2 valid? No. Okay. Is a 3 valid? Yes, it is. And we proceed further. Now, this doesn't mean that this is actually where the 3 lands and this is actually where the 2 lands. You're going to see why. And if I fill in a 1 here, that's not valid. All right. We're going to fill it in with a 2, and that's not valid. We're going to fill it in with a 3, and that's not valid. We're going to fill it in with a 4, and that's not valid. And because we've reached a 4 here, and this is a 4x4, that means that there can't be any values here, which means that this 3 right here, by definition, cannot go here. So we're going to fill it in with a 4. And is a 4 valid? No, it is not. So now we're going to go back, and because 1 was not valid, 2 was not valid, 3 was not valid, and 4 was not valid here, now we're going to go back here, and we're going to turn this into a 3. And is a 3 valid? No, it is not. So now we're going to do 4. And is 4 valid? Well, yes, it is in this instance. And now we're going to keep doing that, and so on. And if it turns out this 4 isn't valid, then that means that by definition, this whole entire board is impossible to solve. Now, how does that look like? So we start off with this little thing right here. And let's just say this is here. So we start off with our board, and we're going to generate a 1. And we said that, that's kind of ugly, sorry. All right. We said that the 1 wasn't valid, so we forget about that. And we're going to generate a 2. And that 2 was valid, right? So from there, we proceeded further. And then we generated more things, right? We said this one wasn't valid, this one wasn't valid, but this one was. And then this one wasn't valid, this one wasn't valid, this one wasn't valid, and this one wasn't valid. Remember, we reached that instance with this 2, 3, and 4 here. So that means that this, by definition, isn't valid. And if we go here, and then it turns out this one isn't valid, then we go back here, and we know this one isn't valid. And then we do that. And then that one was invalid. And then we proceed further. And then we cancel out. And then we keep searching and searching and searching up until there's 1, right, that is valid and is complete. Then we can sort of backtrack the answer all the way back to here and say, okay, because we found one of the paths where it is valid and it's complete, we've solved it. Perfect. But if it turns out this one was invalid, then this is impossible. And that's what we're going to be making our brute force thing. So we're going to go in here and we're going to make it in C++, right? So I just included the standard IO stream using namespace std. Now, if you don't know what IO stream is, it basically allows you to input and output things into your program. Yeah, so we're going to start off with our main function, and we're going to actually, what we're going to need as well is we're going to need to include vectors. And this is how we're going to basically store our values and everything or whatnot. All right, so what we need to do is we need to find a way to input into our board, right? So first, let's declare our vector int board. All right, and this will create a brand new board. And the reason why we're doing two vectors is because it's two-dimensional. And our board is gonna be of size, at least is gonna be of size n, right? Now what I'm gonna do is I'm gonna make a constant, int const n equals 9. All right, yeah, sweet. Another thing I'm going to do is I'm going to make int const little n. I'm going to make that the square root of this number right here. Okay, so we declared a brand new board. And now what we need to do is we need to input our numbers. So for int I equals 0, I is less than n I plus plus. For int I equal, for int j equals 0, j is less than n, j plus plus. So what this is basically doing is I'm gonna create a brand new board. And imagine this is a 9x9, right? So you have, actually I'm gonna make this like this. And just imagine there's 3 different boxes inside here. Okay, so what we're going to do is we're going to go through each instance. And this will be I and this will be j. So here's how we're typically going to do it. So this right here is our vector, right? And this is row 0, this is row 1, this is row 2, this is row 3, and so on up until row 8. Now it's 8 here, even though it's a 9x9, but remember we started with a 0. Now, so for every j, we're going to fill in here, we're going to fill in here, we're going to fill in here within this row I equals 0. And then after that, we're going to fill in for row I equals 1, and so on. So you're going to see a lot of these for loops within for loops, and these are called nested for loops. So now what we'll simply do is we'll take an input, we'll cin input, and we're gonna, so actually we're gonna make a checker where if input is greater than or equal to 0 and input is less than or equal to n, and this is to make sure we don't get invalid inputs, right? Then what we'll do is we'll take our board and we'll push the value into it. So push back, board I dot push back j. Sweet. And if it doesn't meet that criteria, then what we'll do is we'll say invalid inputs and L, and then we'll return -1, right? That means our program will be canceled and says invalid inputs. All right, sweet. So just like that, we have our board. We have our input board, and what we need to do is I want to make sure whether or not this input works, so we'll create a new function called print board, and it'll do the same thing. Vector int board, and for int I equals 0, I is less than n, I plus plus. What is wrong with me? Okay. And then another one for int j equals 0, j is less than n, j plus plus. Cout board I j, and then we'll print a space bar, sorry, a space between them, and that'll be it. And actually, within here, after this instance, we'll print a new line. And now what I want to do is I want to see out a new line and then print board. And yeah, so I'll create a new tab, G++ Sudoku solver, CPP. And here's where we already find, yeah, bugs. Okay, so this is not supposed to be here. This is supposed to be the other way. I keep getting confused. That is supposed to be right here. Right. There's going to be a lot of times where we're going to have problems. Oh, yeah. You see, I don't fully close these brackets. So that's why we're going to keep compiling it over and over again, just so we can weed out the results. So here I have an example puzzle. So I'll copy that in, paste it, and it should reprint it out. And I don't know why it does that. 0, 1, 2, 3. Oh, okay. I know what issue we have. So our inputs aren't actually inputs. We're actually pushing back into J. And that's already a bug. Board.pushback input. There we go. Because we're asking for an input, so we have to put that input into it. So that's already a bug. All right, dope. So it reprints our board, and that's perfect. Awesome. So that means our input works, and it means our print works. Now, the next step we need to do is, remember how in here we checked whether or not if each row, if each column, and if each box was valid? We need to make a function that determines that. So what we'll do is we'll create a new function called, and it'll be a Boolean checkboard, and it'll take a vector of an int board, and sweet. Now what we'll do is if check row board and check call board and check box board. And we're gonna create these functions, but for now, yeah. So if it checks, so if every row is valid, if every column is valid, and every box is valid, then it will return true. Else, return false. And that's our checkboard function. Now what we need to do is we need to create a check row function. So that'll take a vector of an int board. And what we'll do is we'll create int. Let me think. Okay, we'll create an array. Int r of n. And what we need to do is we have this array, right? And this array will be 9 long, right? So it'll be 9 long. Sweet. And now what we'll do is we'll have to put these values into the array. So for int j equals 0, j is less than n, j plus plus, and because these are rows, what we need to do is r of j equals board I of j. So what I'm doing here is I have, let me remove this. So what I'm doing here is I'm gonna evaluate each row individually. Actually, it'll be easier if I create a 4x4. So this will be that. And then I have, say I have 1, 0. Actually, imagine this is a 5x5 or a 6x6. Even though it doesn't make sense, just bear with me. So imagine you have a 1, 0, 3, 4, 3, 0. Right? So what I'm gonna do, and then this is like something different. Okay, so because we're checking by rows, we need to take each row individually. So this first thing right here is it declares a brand new empty array. And what we're going to do is we're going to extract the array, and we're going to, for every row, we're going to move that thing into a brand new array. 4, 3, 0. Right? So this is what our array will look like. And it'll do that for every instance. And now what we need to do is we need to check whether or not this is valid. And the way we'll do this is we will sort. So because this is a copy, we can sort this little array to display this. 0, 0, 1, 3, 3, 4. All right. And what we'll do is we'll take the second element of it, and we'll compare it to the previous one. And 0 means empty value, so we can forget about that. So we can tell it if it's 0, skip it. So it's 0, so we can skip that. And now we'll do a 1. So is 1 equal to 0? No, it is not, so we can proceed. Is 3 equal to 1? No, it is not, so we can proceed. Is 3 equal to 3? And it is. And if we find out that it's equal to the previous one, then by definition, that is not a valid board because there's already a duplicate. Now, let's take this example, for instance, where we have 0, 0, 0, 3, 4, and 1. We'll sort that bad boy to be 0, 0, 0, 1, 3, and 4. All right, dope. And what we'll do is we'll take the second one and we'll compare it to the previous one. But is it a 0? Yes, it is, so we can skip it. Here, is it a 0? Yes, it is, so we can skip it. Now, why are we skipping? Well, 0 means, in our definition, it'll mean an empty value. And obviously, there can be more than one empty values within each row. So that's why we're skipping that. And then we can compare 1 to 0. Is 1 equal to 0? No, it is not. Is 3 equal to 1? No, it is not. Is 4 equal to 3? No, it is not. And because we've reached the end, that means that this row is valid. So that's what we're going to do. So this thing right here, what we're essentially doing is we're creating this part of it. So we create a brand new array. And now what we need to do is we need to, so this will create array. And now what we need to do is we need to evaluate the array. And what we're going to do is we're going to sort the array. So sort R plus N. This is how it sorts. I'm not sure which sorting algorithm C++ uses, but that's irrelevant. We just sort it. And actually what we need to do is we need to include a new library called algorithm. And that's what allows this function right here to be possible. So we'll sort our array. And now what we need to do is for int j equals 1, because remember we have to start at the second element. And the reason why we need to start with the second element is that we're always comparing it to the previous one. If we start in the first one and compare it to a previous one, there is no previous value. So this thing is going to break. So for int j equals 1, j is less than n, j plus plus. All right. So if actually what we'll do is this: if array at j equals 0, then continue. If array at j equals array at j minus 1, aka if this number is equal to the previous one, then by definition return false. And if it goes through that, oh wait, sorry, we need to do, oh shoot, for int I equals 0, I is less than n, I plus plus, and then we can write all of our stuff here. All right, so there was a bug I made, and the bug was that I was doing all of this stuff, but I need to, wait, I'll delete this line here. So I need to evaluate for every row. And so this I right here will represent which row we're at. So that's why this I was here. I just forgot to implement it. Nothing big. So yeah. And now if it goes through this for loop and it completes it, then sweet. There's no issues. Now, if it completes this entire for loop, then return true. And that means we've never encountered this false ever. And if we've never encountered this false ever, then that means that it's true. All right. Now, what does this continue mean? This continue means proceed with the next iteration, and it doesn't mean continue to this. So that's why if it's equal, if this thing equals 0, then we can immediately tell it to skip it. I think a better name would be skip instead of continue, but that's just me. All right, dope. So just like that, we've done it. Dope. Now, I think what we can do is we can see out check row board and okay, what I'm gonna do is I'm gonna test whether or not this function actually works. So g++. Okay, wait, sorry. We need to comment this out. And we need to comment it out because these functions don't exist yet. Okay, so we'll take our input, we'll paste it. Oh shit. Whoops. All right. So this thing right here outputs a 1, so it's true. Dope. Now let's do a test case where this is a 1. Sorry, this is a 2, and that makes this invalid. We'll copy that. A.out, paste it, and this should output a 0. Awesome. So it works. So we can get rid of that, and now we know that this thing right here works. So how do we do it for the column? It's just simple. We take 18. So all we need to do is we need to copy it. 18 to 31. This is just a vim command, so don't worry about that. And now, whoops, what did I do? Why did I do that? 18 to 31. Awesome. And the only thing that actually changes is the way in which, so this array and stuff is still the same, but the only thing that changes is how we copy this in. So if we have 1, 3, and then a 4 here, this thing will now be a 1, 0, 1, 3, 4. And we'll still do the same stuff or whatever, but just the way in which we get the information will be different. And this is where we get our information from. So the only thing we need to change is that and that. And that should work. Awesome. And now what we need to do is we need to create bool checkbox. Again, vector int board. And this one will be a little trickier. All right. Now I want to write the checkbox function in a very specific manner. And the reason why I want to do it in a specific manner is because I want to make the Sudoku solver not just a 9x9, but I want it to be 4x4, 16x16s. I want it to take that. And this checkbox function, it's actually a little tricky, and it took me a while to figure it out. But let's see if I get stuck again. So what we need to do is, so this is a 9x9. I'll make it a little smaller. These are the boxes. So I need I is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We're going to first start off with our for loop. So for int I equals 0, I is less than n, I plus plus. Again, we'll create our array int rn. And then, okay, so we've created our array. Now, for int j equals 0, j is less than n, j plus plus. And now this is where we're going to fill in our box. Now, this is I equals 0, I equals 1, I equals 2, I equals 3, and so on. But the important thing is that within here, the coordinates for each box, now imagine these are little tiny, I'll make this a little smaller. So 9.4, I'll make this a 2. Yeah, so these are the little boxes, right? Inside this. I think it'd be better if I do that. All right, sweet. So these coordinates right here, I equals 0, I equals 0, I equals 0. I'm talking about the the row. So this right here, the row number is 0, but this is 1, 2, this is 3. And then this is 1, 0. Whoops. It's supposed to be 0, 0. And this is supposed to be 0, 1. And it's supposed to be 0, 2. And this is supposed to be 1, 0. It's supposed to be 1, 1. And 1, 2. Now, I think a better way to visualize it is not if we use that, but if we use this, like a different value, right? If we, instead of I equals 1, let's say I is equal to 3. So this should be 3, 0, 3, 1, 3, 2. Now, how do we determine what to place in here? So board, and this will be our row, and this will be our column. Now this function is a little tricky. So for I equals 0, notice how this first number, this row right here, we're always instancing a certain amount, right? So here, when I is equal to 0 and j is equal to 0, the number we have to output for this first thing right here is a 0. For j equals 1, that should output a 0 again, right? For j equals 2, that should output a 0. For j equals 3, that should equal a 1. All right, now we're getting somewhere. Now, the important thing to realize about these rows is what we can do is we can say, all right, well, obviously, this is a product of whether or not 3 is divisible by 3. Or not divisible by 3, but we floor this, right? So 3 divided by 3 in computer science terms is 1, right? And it is mathematically 2. And 4 over 3 means 4 over 3, right? But if we take this as an integer and we take this as an integer and we output the answer as an integer, the actual answer is 1.333 recurring or whatever. But because we take this value as an integer, this is actually going to be 1. Believe it or not. And even if it's 1.666 or whatever, that's also going to be equal to 1. Right? So ultimately, I don't want you to think as this of this as a the actual answer. I want to think of it as flooring it. And what we'll do is we'll take this I and we'll floor it and then multiply it by 3. And that's how we'll get this number right here. And then we'll add it by flooring this. Believe me, this works, and it took me a while to get it, but let's just do it. Actually, this could be a one-liner. Board, and what we'll do is we'll say I divided by n, and this is why we need small n. So small n is the square root of that. So where is it? Okay. I divided by n times n. This is why it's a little counterintuitive, because mathematically speaking, this would cancel out. But in this case, this is not it. So say I is 5. So 5 over 3 times 3 should equal 5. But in this scenario, it's 3. And that's because 5 over... Oh, sorry, it should be 3. Because 5 over 3 is equal to 1. Not 1.66666. And then 1 times 3 will equal 3. Awesome. So that is how we do this first part. And what we're going to do is we'll add it by j divided by n. And that'll do that. Now, typically speaking, these dividing things or these flooring things are very common when you want to access rows. So this is why this will be the dividing symbol. Now, for the next part, for the column, we're going to use a mathematical function or operator, called modulo. And what modulo means is the following. So if I have 0 modulo 3, it just basically means that if I divide this by 3, what is the remainder I'll get? And that will be 0. And if I do that divided by 3, I'll get a remainder of 1. And so on. Now, let's take 3 modulo 3. That will be 0. Because 3 divided by 3 is 1, but has a remainder of 0. That means that if we take 7 modulo 3, that will output a 1. 8 modulo 3 will output a 2, and so on. So we'll keep getting 0, 1, 2, 0, 1, 2, 0, 1, 2, and that's what we're going to need, all right? So for this, we're going to do I modulo n. We'll wrap this around in some parentheses, and then we'll multiply this by n, and then we'll add it to j modulo n. Now this part, right, it sounds like a whole load of gibberish, right? Rj is equal to board, blah, blah, blah. But just try to find the logic in it. Actually, we'll try to find the logic ourselves. So this is our... I'll explain why that's the case. The beauty of it is finding it out. And it took me about 20 minutes to figure this little equation out. It could take you less, it could take you more. But the point is that once you find it out, believe me, that stuff is satisfying. All right, so let's take a 9 by. Okay, so we'll split this into little things. We'll split that into that. Now the important thing to realize is I will determine which box number we're in. So this will be, for I, this would be a 0, this would be a 1, this would be a 2, this would be a 3, and so on. And then within this little thing, there are little coordinates, right? So there's going to be these little boxes. Whoops. A box here, a box here, a box here, and a box here. Sweet. And the coordinates of this is 0, 0. And the coordinates of this is 0, 1. And the coordinates of this is 0, 2. And so on. So this first, so the J will tell us the instance. So even though these are the coordinates, I want you to separate the concept of I and the concept of J. I want you to think of I as the box number and J as the element within the box number. And I want you to think of this as the row, and I want you to think of this as the column. And we said our thing was gonna be row divided by n times, oh sorry, okay, I think it'd be easier if we say 3 instead of n. R divided by 3 times 3 plus J, oh sorry, I plus J divided by 3. Alright. And I'll take this one as an example. I think once we move to boxes outside of that, it'll be a little easier to understand. So this first equation right here, this is to find out this number right here. Right? So, okay, so this should be 6, 3, 6, 4, 6, 5, 7, 3, 7, 4, 7, 5, and that should be 8, 3, 8, 4, 8, 5. Awesome. All right. Where is it? Where is it? Okay, let's do this one actually. So in this case, I is equal to 2, 4, okay, wait, 0, 1, 2, 3, 4, 5, 6, 7. So I is equal to 7, right? I is equal to 7 because we're in the 7th box. And right in here, J is equal to 0. So for J is equal to 0, the number we have to output is a 6. That's the number we have to output because we're focused on this first number right here. No, not that one. We're focused on this number right here. All right. So let's take that. So I divided by 3. So 7 divided by 3 will give us 2. Remember, it floors it. Times 3 will equal 6 plus 0 modulo, 0 divided by 3 will be 0. So that will output 6. Awesome. Now let's move to J equals 1. And that should also output a 6. Dope. And if we do that, 7 divided by 3 is 2. 2 times 3 is 6. Plus 1 divided by 3 is 0. So that should equal a 6. Awesome. Now let's move to this one, right? Let's move to this one. I think it'll be easier. Okay, let's move to this one and then move to this one, just so we see where it actually changes. All right, so I is still equal to 7, but J should equal, in this instance, 0, 1, 2, 3, 4, 5. So for that, we should output 7. So forget about that. That should be 7. So for J equals 5, and that equals that should equal 7. So 7 divided by 3 is 2 times 3 is 6. 5 divided by 3 is 1, so 6 plus 1 is 7. Awesome. Now if we make this a 6, this should equal 8. And if we do 7 divided by 3 times 3, that's again 2. This 7 divided by 3 is 2. 2 times 3 is 6. Plus 6 divided by 3, which is 2. 6 plus 2 is 8. Awesome. That's why this works. And if you don't believe me, you can try it out for any part of the board. Now we can move on to do the other equation. And our other equation, if I'm not wrong, was I modulo 3 times 3 plus j modulo 3. And again, we'll use these ones as an example. So this should be 0, 1, 2, 5, 6, 7, 3, 7, 4, 7, 5, 3, 4, 5, 3, 4, 5. So now we're focused on the second number, right? And this is our equation. So I equals 7. J is equal to 0. Dope. Wait, is that the function we came up with? Yeah, it was. Sweet. Okay, so this number should output, number should output a 3. Now let's do it. 7 modulo 3 will equal 2. 2 times 3 is 6. 7 modulo 3 will equal 1. I'm sorry. So 7 modulo 3 equals to 1. 1 times 3 equals to 3. And then 0 modulo 3 is equal to 0. So 3 plus 0 is equal to 3. That works. Now let's move to j is equal to 1. That should output a 4, right? So 7 modulo 3 will equal to 1. 1 times 3 will equal to 3. So we can do that. And then 1 modulo 3 is equal to 1. So 3 plus 1 is equal to 4. Now if we do j modulo, 2, right? So that will always be the same. And 2 modulo 3 is equal to 2. So that should output a 5, and it does, and so on. And now if we take that as a 3, now that should output a 3 instead. And because we already saw that this equals 3, 3 modulo 3 equals 0. So 3 plus 0 is equal to 3. That works. And so that's why this equation works. And actually, what we'll do is, just to ensure that it works, what I'll do is I'll print a brand new function. I'll print for int j equals 0, j is less than n, j plus plus. Cout rj plus, and then cout and del. And just to prove to you that this works, we'll recompile it. So clear it out. All right. So, oh, whoops. I didn't do anything about that. What we'll do is we'll check box board. All right. Sorry, we'll recompile. Whoops, I'm sorry. We'll recompile it. A.out. We'll copy this thing into it. Paste it. And if we see here, let's take, okay, actually, it'll be easier if we use the solution. So let's take this box, for example, 957 483 612. Yep. Let's take our second box, 613, 257, 849. 613, 257, 849. Yep, that's here, and so on. So our checkbox works. Well, our checkbox works, but now what we have is we've created our array. So we've created our array. Now we need to evaluate our array. Eval array. So we'll sort it. So R and then R plus N. And then for int j equals 1, j is less than n, j plus plus. If r j is equal to 0, then we continue. If r j equals r j minus 1, return false. And then complete that. Whoops. And then if we finish our for loops and we have no issues, then return true. Awesome. And just like that, our checkboard should work. And what we'll do is we will test it. So cout checkboard board. And whoops. No. Or actually, what I'll do is awesome. Let's recompile that. /a.out. Now this should be completely valid. So this should output a 1, and it does. This should output a 1 because it's valid as well. Right? Doesn't mean it's solved. Oh, okay, it's not valid. And that was because I changed this one. Yep. that goes to show that our function actually works, which is awesome. We'll clear that. So our row works. Let's see if our box works. So that, we'll change that to a 2 to break this box thing. Out. Whoops. Out. That should output a 0. Sweet. And let's make sure the column thing is broken. So .a.out. Paste. Alright, sweet. That's a 0. So we can change that. And let's just make sure that our original puzzle is solvable. Alright, awesome. So now we have the checkboard function complete. Now what we need to do is we will now create our solve function. And what I'll do, I'll make it as a boolean. So bool solve board, and I'll take a vector int ampersand board. So this, now if you don't know what ampersand means, I want you to think of it as basically what it does is that will modify the actual value of the board. And we're doing it by accessing the actual memory address of that board, or where this board is stored, and then changing it through there instead of creating a new copy. So what this does is it creates a brand new copy of the board, right? And this creates a brand new copy, and this creates a brand new copy of a board. But this takes the physical board that you're given. So if we input the board, the function will create a copy of it and then manipulate that copy. But since here we need the actual board, we need to have this ampersand because we need to actually mess around with the board. All right, dope. So what we'll do is we'll create an if statement. So actually what we need to find is we need to find the next available space, because I don't want to do a for loop and then evaluate that. That'll be kind of useless. But we're still doing that anyway. So what we need to do is we need to find the next space. So int next available space will equal find next space board. All right, dope. That means we need to create a new function called find next space. Find next space. And it'll take a vector int board. And what we're gonna do is we're gonna create a for loop. So for int I equals 0, it doesn't matter, we still have to make the for loop. For int I equals 0, I is less than n times n, I plus plus. And the reason why we're doing n times n is because n here, it's the dimension, right? So if it's 9, then we need to search for 81 different possible ones. So for that, okay, if let me think this through. Find next space. Okay, so we need to go to the board, and again we need to do this stuff, but remember how we said this is rows will always be dividers, and then columns will always be modulos. So what we'll do is if board I divided by n, right? Because here it's up to 81, so we don't have a second parameter. We have j. And then here it should be I modulo n. So that's how we'll find the actual index of it. And what this means is, so if it's I equals 0, 1, 2, 3, 4, 5, 6, 7, 8, this should still output 0. And 8 divided by 9 is 0. 0 divided by 9 is 0. So that stays true. Then when we have 9, so 9 divided by 9 is 1, and that's why that's true. And then same thing here, but for the modulos. So that's why that's that. This one was a lot more messed up because we were kind of doing a box within a box. Sorry, we were iterating inside a box, and each I was a box itself instead of it being a row and a column. That's why this thing was a lot more confusing. This one's fairly simple. So if board I divided by n, so if that equals 0, right? That means we found an empty space. Then we'll return I. I don't think this is a nice way of doing that. Yeah. Whoa, my bad. So for that, and if we go through our entire for loop and we don't find empty spaces, we'll return -1. And the reason why I'm going to return -1 is that for me will indicate that this thing is complete in a sense. So what we'll do is this. We will go and we'll search. So solve board. Okay, if next available space equals -1, aka the board is full, then we'll return true because the board is filled in and it's complete. Now you might be worried about, hey, don't we have to check before we insert? And you're right, but we'll write that function elsewhere. All right, so what we'll do is we'll create a new for loop. So for int I equals 1, because now we have to start at 1. I is less than or equal to n, and this time we're going to include n because we're going to insert I into our board. I++. So this is where we start generating our thing. So once we do that, now what we're going to do is we're going to create a function. We're going to ask, can insert board, right? Can insert board, the index next available space, and then I. If can insert board. So we're going to create this function called can insert board, where we'll take a thing and then we'll say, okay, is it possible if we insert it, and it checks it inside here. Sweet. And if that's the case and we can insert it, then we'll insert board next available space I, right? Dope. And now what we'll do is we will create an if statement. So if solve board, this is where we use our recursion. So if solve board is equal to true, then what we'll do is we'll return true. Oh, sorry. Yeah, we'll return true. Dope. If that's not the case, else what we need to do is we need to go back and reinsert our board. Insert board next available space and change that to a 0. Now, all of this sounds like a load of gibberish. Oh, wait. Return false. Okay. I went and did all of this despite not making these two functions, but I want you to see the logic behind it. Okay. So what I'm going to do is I'm going to create a brand new one. I'm going to make this 9 pixels. Dope. All right, let's take a 4x4 as an example. Now this was a 1, imagine this was a 4, this was a 3, this was a 2. Okay, so this first thing starts off with int next available space, right? And what we'll do is it'll find the next available space, and if it's full, then return true. Else, if can insert board. So what I mean by that is we're going to see can insert board and can we insert this? And I'll create this function and this will say, nope, you can't insert it. So because that's the case, we can skip that. And now, right, so can insert board. If this is false, then this whole thing won't proceed, and then we'll proceed to I is equal to 2. So I equal 2. Can insert board? No, it cannot. So that won't run. And now we're going to do I equals 3. And then I equals 3. Can insert board? Yes, it can insert a board. So this thing is true. So what we'll do is we'll insert 3 into it. Right? We'll insert 3 into it, and then we'll proceed further. But what we'll do is if solve board, all right? If solve board. Now, this is really, really, really important. This line right here is how we solve our, this is pretty much our program. This little line right here. This is the most important line of the entire program. And that's because if you realize here, this is calling itself. And this is what we call recursion. So this, what it'll do is that, okay, sweet. So inserts that thing into it. And now I want to solve board. And now what I want to do is I want to solve board, but now I want to solve this board. So whereas last time we wanted to solve this board, now we want to solve this board, right? And then we proceed further. Can insert board, can can do this, and so on. Now, here's the thing. Remember, here, 1 is not possible, 2 is possible. All right, dope. So now we're going to solve board this. Now, does this sound familiar? So if can insert board, nope. Can insert board, nope. Can insert board, nope. Can insert board, nope. It can't. And here, you see how we went through 1, 2, 3, and 4, and went through 4 different times without ever, doing this code? That means at the end, we're going to return false. And this right here is an if statement where it asks whether or not this is false. And if it is, so yeah. So if it's false, then it won't do this. And because that's false, we're going to do this. And what this does is it simply undoes this part. So this is basically an undoing. So, all right. Oh, whoops. This is undo previous insert. Right? Because now we're replacing our space with 0. And then now we can go back to our instance and do that. Can insert board, but now it's a 0. This thing undoes it. But now let's take the example where this is now all true. So say 4, this is a 3, this is a 2, this is a 2, this is a 1, this is a 1, this is a 4, this is a 3, this is a 3, this is a 2, this is a 1, this is a 4. All right. Now, actually, I'll leave this last one blank. Let's take this case where we have this board, right? Now, what it'll do is, now can insert board. Okay, we have this board, and we give it this board. So find next space, and it'll find this space. Now, if this is full, return true, but it doesn't return true. Okay, so we'll proceed here. If I equals 1, can insert no. Sorry. Can insert no, can insert no, can insert yes. All right, sweet. So now what we'll do is, so this can insert, yes it can. So we'll insert it. And now if solve board, board. And now we're going to give it solve board, and we're going to solve board, and we're going to recall it with this board, right? And this is our base case, right? So now we look at it, and look at this. Now we give it this board, find the next available space, and this next available space is going to return a -1. And so if next available space is -1, then return true. And because this returns true, then this previous one we had returns true. And once again, if we backtrack it, remember we had the thing where we had this, and we had that, and we had that, and we had that, and we found the chain. Now we've found one that returns true, right? So that means that because this returns true, this will return true. Then this will return true, then this will return true, then this will return true, and this will return true. And all the little instances we had will keep collapsing this way. That's recursion. And because they collapse that way, that means that this returns true. And remember that we were modifying the physical board? that means that we've modified it to the point where now this is the complete board. And just like that, we've solved it. So now let's not get our hopes up, because now what we need to do is we need to code the can insert board function. Can insert board. So this will take a vector int board. And this time, I don't want to make it the ampersand, because this time I do want to create a copy, right? I want to make that a fail-safe feature. So yeah, this time I do want it to create a copy. All right, so next available space. So int next available space, and then int num, right? Can insert board. All right. So what we'll do is we'll insert board next available space, and we'll insert num into it. Now, if check board, you see how we're checking the board? So this thing already checks the board for us, because we're checking it within this little function here. So if check board, board, and if that outputs true, then return true. Else, return false. And just like that, we've created our can insert board. W, sweet. And now we need to create an insert board function. So we'll create void insert board, and that'll take a vector of a vector int board that will int index int num. Actually, this is wrong. This is supposed to be ampersand, because we're trying to modify the physical board. Sorry, we're trying to modify the physical board. Okay, sweet. So insert board. Now what we'll do is we'll simply say board index divided by big N at index modulo N, this is a vector function, equals num. And just like that, we've created it. So we're telling it at this element, make it equal this instead. And just like that, we have solved we have created our Sudoku solver. Now this might have some bugs. Sudoku solver. Yep. Expected something. Wait, what are we missing? Wait, let me see. Ampersand board. Okay. Solve board. This is not supposed to be a semicolon. It's supposed to be a comma. That means that's supposed to be a comma. Coronavirus. Okay, this again is supposed to be a comma. All right, sweet. ./a.out. Okay, wait, no, actually, we haven't done it. We haven't actually completed it because we haven't actually called it. Okay, so what can we do? So let's just say what we'll do is if solve board, if that's true, then we'll print board. We'll see out a brand new line. And sorry. Let's print a brand new line first. See out and L. The reason why I want to print a new line is I don't want it to be mixed with the input. Okay, if solve board, if that's true, we'll print our board. All right, sweet. So we'll print our board, print board. And the reason why we can print our board is because the solve board solves it and it changes the board as it goes along. Awesome. But if this returns false, and it returns false for all iterations, else, then we will see out this board is impossible to solve. And we'll end and just like that, now we've created it. So let's save the sweet stuff for later. G plus Sudoku solver. All right, awesome. A dot out. So this should output this solution, right? Paste, and that pastes that. Awesome, right? Because the solution to a complete board is a complete board. Now, if we do this, copy, /a.out, and we give it this, it should output that. See how it takes a bit? It's calculating. Takes a while. We can obviously make this more efficient, but the point is we want to solve our board. Hopefully it works. Actually, it takes a bit of a while. It's actually taking a while. I want to make sure that, let's see if we have, is this not running on an endless loop? Let me check. Okay. Oh my goodness. Yeah, so here's the problem with backtracking and not making it more efficient is because you're generating so many different things, so many different numbers and stuff. It'll take a while because each thing becomes exponential. And actually, the best way to do it is, remember how we were solving for where we were like canceling out and finding out the stuff that like mattered and stuff? Well, we should do a function that does that first and gets the board to a point where all the obvious values are solved. Okay, you know what I'll do? I'll cancel that. I'll input this, but I'll input it with a 0, and that should output it as 9. And that way I'll know it works. Yeah, it works. So it gives it a 9. All right, and that, I'll change that to a 0, and I'll change that to a 0, and I'll change that to a 0. Copy, /a.out, paste, and yeah. Okay, sweet. So it does give the solutions, right? But it's just very, 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 very inefficient. Yeah. So that was how to brute force a Sudoku solver. What we can do is next video we'll optimize the Sudoku solver to make it run at a much faster speed. All right, guys, thank you so much, and I'll see you on the next one.